Okay, I will give you your exams back at the end of class. I haven't put the scores into Canvas. I will do that sometime today. I don't curve individual exams, but I may curve at the end. I don't know what to do with this exam right at the moment. And you won't have the benefit of having your exam boosted up by participation in the in-class stuff yet, until I get that online. Okay. I will post the answer key sometime today, but my suggestion is take a look at what you missed, try and figure out what that is, because that'll help you learn it for next time. Then if you have any questions, come and see me. Okay, chapter 5 is dealing with confirmations of ethanes or ethane molecules, and also cyclohexanes for Friday. So I did put a video at the beginning of the 5.1 that's my video. From here on out, I probably will have videos that match up with the course content, and I'll put those in the book and also in the course in the Canvas folder as well, so you can use those in addition to reading the book. I just didn't have those for the first 3 chapters that the way this book's written. All right, so basically the idea is confirmations, and the first thing that we have to really be able to do is to be able to look at what's called a Sawhorse projection. And there's 2 kinds of Sawhorse projections, and be able to convert those into Newman projections and tell me whether or not they're staggered or eclipsed. Okay, so if we had, for instance, groups A, B, C, D, E, and F, and I was over here looking down the carbon-carbon bond, could I draw the Newman projection of that molecule? Yes, no? If yes, go ahead and do it. Then we'll check. And then if you get that one done, then you can try the one on the right. Okay, I've set it up to be able for you to be able to draw in your left, the left-hand structure that I had. Yeah.
Was that by chance for the mic class?
Probably. Which is gonna suck because now I'm gonna have to take it, I'm gonna have to copy it over. Copy to section 2. Where does it go? I can't do drawing on the flies, so I can only do ABC on the fly. Section 2. Stop. The hell it's drawing it. Okay. The one on the left. So, Newman Projections have a front where the 3 lines intersect. That's the front carbon. Then they have a circle, and the circle is the back carbon. So if I'm going to orient this molecule from the left, the key bonds are the bonds that are in the plane of the board, which are those 3. Now when I look at those down, the carbon-carbon bond, the front carbon is going to look like that with an A, and then B is behind, so it's to the left, and C is in front. So when I'm looking at the end, when I'm looking at it end on, that's how I get the Newman projection. But the Newman projection that I drew it from, it's as if I'm over here looking into the center of the CC bond. And then the other 3, F is in the same plane as A. And then we've got D over here, and I've got wait, hold on. I've got D there, and then I've got E over here. Now, how did I know that? Well, if I'm looking at it and picture it left and right, but also because D and C are both on the bold wedges, so they would be coming towards me if I'm standing over here, and then E and B are on dashed wedges, and so they would be behind me. So this is the way those 2 pictures interchange. If I'm over here, I'm drawing this structure. If I'm on the end looking down, I'm drawing the Newman projection. Okay. And that would look like this. So if I'm writing out this molecule, I'm looking at it like that. So the front carbon is obscuring the back carbon. So these 3 hydrogens are towards you, these 3 hydrogens are away from you, but you can kind of see if I tilt it like that. So that's the first one that we're looking at.
What's the name of that app?
This app is called It's called iSpartan. It's not cheap. It's like $20, I think. I mean, that's probably a weekend, but of fun activities. But it is pretty good from that standpoint. So, and we have the PC version of this upstairs in the Carabine computer lab. It's called Spartan Student, so that you can actually draw these out. And we'll do this in lab at the end of the semester. And you can also go online and find different pictures, three-dimensional representations. But that's what this is. So what this allows me to do then is, I can look at it this way too. So that's the first confirmation that we have. Okay, so is everybody able to draw that? It looked like most people were getting the hang of it. So then for the second one, the telltale sign on how to draw this one is that, again, all three of the bonds in the plane are basically in the plane, but it makes a U shape. So when I'm looking at this one, the front carbon's going to look the same. I'm going to have A, B, and C. But now D, E, and F are all in the same plane as the front carbon group. So in other words, D is in the same plane, F is in the same plane as C, and E is in the same plane as B.
Would it be okay if we wrote the things like D and F like on the other side of the front carbon? Like if I wrote D to the left, it makes it to the right. Isn't it still eclipsing?
D's got to be eclipsing A.
Yeah, I know.
If you wrote it down here?
No, like if I wrote D to the left of A instead to the
Oh yeah, to the left of A is fine. So in other words, it doesn't matter. The reason I can either draw here or here, really, that group would be obscuring the other one, so I wouldn't be able to see it. So yeah, whether you write it to the left or right is fine. One of the things you want to do is, if you're going to write it to the left, then be consistent in like that. So don't write like one to the left and one to the right, because it may confuse you. It may confuse me. If I get confused grading, I don't give partial credit. So that would be what this one looks like. Okay. This one, the one on the left, would be called the what form? Staggered from the reading. So this is the staggered. And the one on the right is called eclipsed. Which one's more stable? The staggered is more stable. So remember, these groups are nothing but big clouds of they're atoms, which are nothing more than big clouds of electron density. So when you have groups that are 60 degrees away from each other, that's as far as they can get. And so that's going to make them that's going to make that more stable. When they're right on top of each other, when the hydrogens or other groups are right on top of each other in the same plane, they're going to be as close together as they can get. They're going to repel. That's going to raise the energy of the molecule. So what we need to be able to do is write staggered and eclipsed confirmations from these diagrams, from these Sawhorse diagrams. And the key to telling whether it's staggered or eclipsed is the position of those bonds that are in the plane. If it's U-shaped, it's eclipsed. If it's, give me some creativity. If I looked at it on its side, kind of looks like an S, maybe. All right, if I look at it this way, kind of looks like an S for staggered. right? If you need to come up with mnemonics to remember that. Okay. If you can't begin to see it in your head. And this is where models come, are sometimes helpful. So if you don't have models and you want like a 2-carbon thing, email me or stop by, because I probably have tons of kits in the office that I could give you a couple of those carbons to go with. And you can just bring them back when you're done. I don't let people use models on the test, because then they play with the models, don't answer questions, and get angry because they get a low score. And anytime you take a standardized test, you're not going to get to use models. So we might as well, you have to be able to see this in your head and also on paper. And there are other ways to look at this. Okay. So you've got to be able to go from here to here, and then be able to tell which one's staggered, which one's eclipsed. Okay. All right, everybody kind of with me on this? So then I would say, fine. So let's make things a little bit more difficult. Let's go to butane. And butane, I think, was in the book as well, but here's butane. Can we write all 6 staggered and eclipsed confirmations, 3 staggered, 3 eclipsed, for butane, and can we rank them according to energy? That's the question I'm going to ask you about Newman projections. Is, can you write all of them for a molecule, all 6 of them, and then rank them in energy from number 1 to number 6? Okay. I always have to give you a bond to look down. Because if I give you any choice, I'd look down the 1,2 bond. Because looking down the 1,2 bond, I see 3 hydrogens and a group, and basically that's the easiest problem you could get, because they all have the same energy. So I'm going to say, let's look down the carbon 2, carbon 3 bond as if I was numbering this IUPAC 1, 2, 3, 4. So I want to look down the C2, C3 bond. So let's start with this. Let's start with the staggered. And I'm going to make C2 the front carbon, although I could make C3 the front carbon. It isn't really going to matter. But now I've got to put my groups on. So what's attached to the C2, which is the front carbon? You got to have 3 things. A what?
A carbon and 2 hydrogens.
Can you specify what carbon? What kind of carbon? In other words, the group. What group?
3.
So what I'd really like you to say is a methyl group and 2 hydrogens. Now, the reason I say that is because if you just say carbon and 2 hydrogens, what if that carbon's an ethyl group? Because the size of the group that's going to be attached to the Newman projection is going to play an important role. So we don't want to shortcut by just writing a C. We want to write the entire group so we get a sense of its size. Okay. So I've got a methyl group and 2 hydrogens attached to the front carbon. Here's my front carbon, here's my 2 hydrogens, and then here's my entire methyl group. What's attached to the back carbon, carbon 3? What? A methyl group and 2 hydrogens. In other words, same thing. So methyl group, 2 hydrogens. Does it matter where I put the methyl groups and the 2 hydrogens? No, because I'm going to generate 2 more staggered eclipses that are going to catch all 3 possibilities. but I got to get the front carbon and the back carbon right. And if and when we get to exam time, this is one of the problems where if you don't draw the structure that I gave you, you basically like make up your own problem, and I don't grade anybody else's problems, I just grade mine. So that means partial credit is probably not happening. So you've got to make sure you can draw the structure first. Okay, so there's one. So now what am I going to do? I'm going to rotate around the carbon-carbon bond on paper. So I got to decide, do I want to hold the front carbon constant or the back carbon constant? And then I'm just going to rotate the other carbon. Me, I prefer the front carbon. So then what I do is I just simply write the groups attached to the front carbon on all three staggered Newman projections. And so now we can rotate clockwise or counterclockwise. So again, I usually work clockwise. So I'm going to rotate this methyl group where this hydrogen is, this hydrogen where that hydrogen is, and the hydrogen over to the methyl. So I'm going to make a 120-degree rotation on the back carbon. If you want to hold the back carbon constant and rotate the front carbon, that's fine. But you got to hold one constant. Because if you don't, what you'll end up doing is rotating the molecule and not catching all three conformations. And since I use that term conformation, the definition of a conformation is, or conformations are, they are different three-dimensional structures that you form by rotation around a single bond. That's what the conformations are. So in this case, that's exactly what I'm doing. So I'm generating different stereoisomers. So if I do that, then let's see, my methyl group comes down here, and then a hydrogen and a hydrogen. And then I'm going to do that again, same direction. So now I've made my three distinct eclipsed conformations.
Are these staggered?
They are the staggered conformations, not eclipsed. So now let's do the eclipsed. So what I then do is I draw three blank eclipsed conformations. And I like to, again, keep one carbon in exactly the same orientation. Well, in this case, the front carbon's going to stay in the same orientation. So I'm just going to put the three front carbons in exactly, or the substituents on the front carbon in exactly the same positions. So now what I need to do is I need to make this staggered into an eclipsed. And so what I need to do is I need to rotate the back carbon by now just 30 degrees so that everything lines up. So I'm going to rotate it counterclockwise 30 degrees so that my methyl groups match up. So that they're in the plane, and then the two hydrogens will rotate back into the other hydrogens. And then 120-degree rotations. So now I'm going to rotate the methyl group down here, the hydrogen there, the other hydrogen there. So now my methyl group comes down here. And then if I did that one more time, I'm going to end up with a third. Okay, so the critical part here is choose a carbon not to rotate, and then rotate the other one consistently in the same direction. Set up your 3 staggered, and then set up your 3 eclipsed. Everybody with me still? Anybody bored? You're bored?
No, I have a question. On a test, would you want us to put in the 120 degree?
No.
Okay.
No, you don't. I'm just showing you the angles if you're into angles.
Okay.
Because you need 120 to convert one into another. To convert from here to here, it's a 60 degree rotation, not a 30 degree rotation. So it's half of that. Okay. So that's the first part. Convert this structure into the 6, 3 staggered, 3 eclipsed. Second part, we rank A through F according to their energies, most stable to least stable. Now, in order to do this, what do we need? In order to do the rankings, what do you need to know? We need to know the rules, right? When it comes to stability, there is no general rule. The stability of tertiary carbocations was different than the stability of alkenes. And so the stability of Newman projections needs a set of rules. And so we need to explicitly write these out in descending order. So, rule number 1 is all staggered are more stable than the eclipsed. The worst staggered confirmation is still going to be better than the best eclipsed. Okay. In the book, they sort of go through these, going from one to the other, kind of rotating the methyl group around, and it creates sort of a diagram that looks like this. Very much like a reaction coordinate diagram, where these things would be the transition states and those would be the intermediates. And so what we really have is the lower energy species are the staggereds, and the high energy transition state species are the eclipsed. I can't draw an eclipsed on my iPad because, well, I might be able to, but I'm not sure that when I actually draw it, it would allow it, because it's such high energy that it immediately moves the groups away. So all the staggereds are more stable than the eclipsed. That means A through C is 1 to 3, and then D through F is going to be 4 through 6 in my stability ranking. Rule number 1. Rule number 2. The rule number 2 is that the more gauche or eclipsing interactions the less stable the molecule is. Now, first of all, I need to define gauche. Or better yet, have you define gauche. What structure on here would be, or give me a structure where the methyl groups are gauche? David? A?
D?
No. No D. C. So A or C show when the methyl groups are gauche. Okay. What does gauche mean? Gauche means that in the staggered form, two groups are next to each other. So in a staggered Newman projection, when two non-hydrogen groups are next to each other, that is what is called gauche. Now, what's D? What about when the methyl groups in D? They would be called steric hindrance. They have lots of steric hindrance, but those two groups are said to be. What's the other one in rule number 2? Gauche or eclipsing. So we would say these guys are eclipsing. Those two methyl groups are as close as they can get. And remember, these are big bags of electron density, or big balloons. And they're going to repel each other. So when non-hydrogen groups are eclipsing, that's unstable. So what we do is we simply count up the number of eclipsing and gauche interactions. Gauche for staggered, eclipsing for eclipsing. And that gives us a ranking of energy. So for instance, in A and C, there's one eclipsing interaction, whereas B, the methyl groups are what we would call anti. They're opposite. So that makes B and C less stable than B. A and C are less stable than B. And for D, D is less stable than either E or F. So what becomes important here is the non-hydrogen groups. Because the hydrogen groups are there. If you're in a staggered conformation, they got to be hydrogen groups that are going to be gauche. If you're in the eclipsing thing, an eclipsing conformation, the hydrogens have to be eclipsing each other. I mean, something has to be eclipsing, so it's better to have two hydrogens eclipsing, two hydrogen gauche, than have two non-alkyl groups. And if the alkyl group is eclipsing a hydrogen, well, that's what's got to happen. So that's not energetically unstabilizing or destabilizing. What's destabilizing is the eclipsing and the gauche interactions. So count them up. And that gives you the second criteria. Then the third criteria is that the larger the groups, that are either gauche or eclipsing, the less stable the conformation. So the bigger the group, the bigger the cloud of electrons, the more steric repulsion there is, the more unstable the molecule. So you can think of these three rules kind of as tiebreakers. although the first one's not a tiebreaker. The second one, if we had two conformations that each had one Gauss interaction, but they were different groups, we go to rule number 3 that says, okay, the two bigger groups, or if one group is bigger than the other, that's going to be the less stable. Having two small groups eclipsing is better than having a small and a large group eclipsing, which is better than having two large groups eclipsing. Okay. So those are the 3 rules then that we have to use to rank energies.
Would A and C, because they have the same energies, would they just be ranked the same then?
Yes, and you said A and C have the same energy. So that's the way you have to think about this. Now you could say, well, aren't A and C the same structure? Not if I keep the front carbon. So A and C, it's better to not think of them as having the same structure, but think of them as having the same energy. And yes, so in terms of ranking, B would be the most stable, then A and C tied, and then E and F tied, and D the highest energy of all. So sometimes we do have ties. So that's Newman projections. And again, the whole idea of these Newman projections is that it gives us a better viewpoint on the molecule. It gives us a better viewpoint than trying to look at the Sawhorse projection. We don't get any kind of spatial recognition when we have like methyl groups in the Sawhorse. We can really see the difference when we go to the staggered in the Eclipsed Newman projections. So it's just a better viewpoint. And if you've been to Ohio State, their chemistry department, one of their buildings is the Newman building, because Newman was at Ohio State when he came up with all this stuff. So I can show you the effects of those two methyl groups looking at this thing again with the light off. Okay, so let me draw a methyl, or let's draw a butane. And let's go into the 3D model of the butane. So there's the 3D model of the butane. And you know what? I did say this was like $20. $20 compared to like the modeling kits. If you're going to buy them at full price, that's it. That is a bargain. But I never suggest people buy modeling kits at full price, because you can go on eBay. If they're $10 or less at half price books, I'll snag them just so I have them in my office to, loan out. So I guess it's not too bad. But what am I going to do? Okay, so if I look at it this way, you can see that those two methyl groups, that's the anti-conformation. And that's as far away as the methyl groups can get. Now, if I want to really see what a methyl group is, I can make what's called a space-filling model, which you can't do with the regular models, no matter how expensive they are. And so this gives you a sense of how big a methyl group is. And so you can kind of see fits perfectly. They're away from each other. There's not, those two methyl groups at the end are not close together. So let me do this. So that is the most stable conformation of the staggered, which is anti. Here's the gouache. So you can see in the gouache, the two methyl groups now are next to each other. And if I rotate this like so, you can see, okay, there is some distance between them. But now let's go to a space filling model, and you can see that the two methyl groups are like really close together. And so that raises the energy of them by, by roughly 3.2 kilojoules per mole. So the gouache conformation where the two methyl groups are next to each other is 3.3, I guess, kilojoules more unstable than anti. Now, if you wanted to put that into percentage terms, like if I had some butane molecules floating around, how many of them would be anti and how many of them would be gouache? 0% would be eclipsed, because that's just too high of an energy conformation. But what you could do is you could go back to general chemistry and say, oh, this energy difference is delta G. Delta G equals minus RT ln K. Calculate the equilibrium constant, which would be something to 1, and then you have your percentage. And if you're smart, you print out a whole table of different delta G values, so that way you can just look it up and see what the percentage is, which I don't have with me at the moment. So that's the butane. So the butane molecule is either going to be gouache or anti. Now, the gouache and the anti terms, you can only say this is the gauche conformation when you have one non-hydrogen group on the front carbon and one non-hydrogen group on the back carbon. Because when I say it's gauche, you have to know your point of reference. If I have 3 non-hydrogen groups attached to the ethane, I can't. But I can say, oh, this group and this group are gauche, or this group are anti. Right? It's kind of like E or Z in cis and trans. Right? So we need a more complicated molecule to work with. And I do have somewhere a homework set dealing with writing different structures, and there's a narrated answer key, and I cannot find it in my Canvas right now, but I know I have it, so I'm going to find it. But let's say that I asked you this problem and said, okay, what I'd like you to do for Friday is a take-home quiz. We went from hypothetical to now concrete. So as a take-home quiz for Friday, what I'd like you to do is to write the 3 staggered 3 eclipsed confirmations of 3,4-dimethylhexane, looking down the C3-C4 bond. It's right there. It's right there. So you're going to have to draw 3,4-dimethylhexane, which hopefully isn't too taxing at this point, and then look down the C3-C4 bond to make your Newman projection, and then draw your 3 staggered, 3 eclipsed. Use the 3 rules that we have, and rank the energies from 1 to 6. If there's ties, indicate that there's ties. Do that on a piece of paper so that I can collect it up at the beginning of class. And we're going to be doing this more often now because I think we need more practice. All right? So that's going to be due on Friday. 3 staggered, 3 eclipsed. Rank all 6 from 1 to 6, highest to lowest. Or lowest energy to highest energy. Okay. All right, exams. So you have to come and get them because according to FERPA rules, I'm not allowed to just put them here and you go through them, which I don't get. Some of my faculty were kind of aggravated about that. Where have you been for the last 5 years? So it's just easier if you come and get them. So Colin, Krista, they're in alphabetical order. Krista, Anthony, Amelia. Sydney, Amber, Sam, Aaliyah, Kevin. Then you can just walk up if you'd like, and then I can give Sam. Yep. Aaliyah, Kevin, Josh, Patrick, Spencer, Sarah, Amanda, Michael, Claudia, Casey, Claudia, Casey, Zach, Carolyn, Ryan.
Just like break down the feedback to those other.
Ryan.
You can easily do it.
Dylan.
Where feelings here, but we're on the
Sydney.
to like.
No Sydney? Hope. Ariana. David. Olivia. Amy. Rob. Jacob. Peter. And Chloe. Or no, Chase, sorry.
You're not gonna look? I looked.
Peter. If you have questions, come see me. I'll put the up at the rent to today.